life can be tough, okay?
Yeah.
And it's not, and it may turn out that some of the experiments that you really need to do in order to answer questions that you're really interested in are really, really hard, okay? Even with string theory, I mean, once string theory gets to a point of development where it's making explicit predictions, these predictions may not be, it may not be possible to make them manifest in experiments that we're capable of doing right now. I don't understand why that shows that string theory is unscientific. Life is tough, okay? Science is hard, okay? Sometimes, it looks like you just can't do this experiment right now, or other times, and everybody certainly hopes this is going to happen in quantum mechanics, it looks like you can't do the experiment, but somebody gets a clever idea, somebody gets a way to trick these theories into exposing their differences in a way that's more straightforward technologically than people had assumed was possible. Everybody hopes this is going to happen.
Hello, this is Robinson Earhart, here with the introduction to Robinson's podcast, number 221. And this episode is with David Albert, who is the Frederick E. Woodbridge Professor of Philosophy at Columbia University, Director of the Philosophical Foundations of Physics program there, and a faculty member of the John Bell Institute for the Foundations of Physics. This is quite whoppingly David's 8th appearance on the show, which makes him the de facto reigning champion among guests. He last appeared on episode 210 with the second in line to the throne, Tim Maudlin, and that episode constitutes, I think it is fair to say, a much more advanced episode on Niels Bohr and the foundations of quantum mechanics. But in this episode, David gives a much more pedagogical and introductory overview of the measurement problem, which is the worm at the core of many, perhaps most, debates over quantum theory. David's most recent book is A Guess at the Riddle, which we discussed in an episode that came out last fall in 2023. And if you're interested in the foundations of physics, then you should certainly be checking out the John Bell Institute, which is providing a home for research and education on these subjects. Any donations are immensely helpful and useful for them, and there's a link in the description. I have to mention a couple of things. First and foremost, I must thank my close friend and teacher, Akile Varzi, for letting us use his office at Columbia to record this. And second, I am extremely embarrassed about this, and I still don't understand what happened, but at one point or another, all of the cameras turned off during this episode. I think it might be related to the fact that it was in the 80s and there was no air conditioning, but luckily David shifted his chair at one point, so I had to get up and check the camera trained on him to make sure he was still in the frame, and that's when I noticed it was off, and I turned it back on, but the two other cameras remained off because I didn't realize this was a systemic issue. Luckily, no audio was lost at all, so if you're listening, you won't even notice this, but if you're watching, there is a period where there's only a black screen, but most of the time after that, or including that, the camera is just on David, and again, I am very sorry about this. I'm distressed about it. I'm embarrassed about it, but it is what it is. Otherwise, I continue to remain extremely close to a 5-star average on Apple Podcasts. So if you're listening, please just take a few seconds to input a rating. Then there is a link to the Patreon in the description in case you want an ad-free feed and show notes. Right now, non-members as well can ask questions for the monthly AMAs, and I want to answer as many questions as I can. So please head over there and put some in for next month. Now, without any further ado, I hope that you enjoy this conversation as much as I enjoyed having it with David. I think, as you know, I'd like this to be a more pedagogical introduction to the
Sure.
measurement problem, though of course there's always plenty of room for philosophy. But before we get there, I don't think I've ever asked this, but how it was that you ended up going from physics, or just being in physics, and then becoming in particular interested in the foundations of quantum mechanics.
My interests were always in the foundations of physics more generally. It was, basically what happened was that I learned more about the professional structure, the contemporary professional structure of philosophy, in a way that made it evident that philosophy departments would be a place where people would be interested in supporting somebody thinking about the sorts of issues that I was interested in thinking about. It was always clear to me that I was interested in these foundational questions in physics. It seemed like the natural thing to study was physics if you were interested in foundational questions of physics. I knew a little bit about the history of philosophy. I didn't know nearly enough about, like I said, the contemporary professional structure of philosophy to realize that those sorts of departments might welcome the kind of work that I was interested in doing. So it was, I got a PhD in physics in 1981. It was very evident at that time that there was lots of hostility in theoretical physics to thinking about the kinds of questions, especially questions at the foundations of quantum mechanics, that were interesting to me. The only person that I knew of, that is the only physicist that I knew of, the only prominent physicist that I knew of, who was doing work more or less in the area that I thought I was interested in working on, was an Israeli physicist named Aharonov, Yakir Aharonov. While I was in graduate school, I got in touch with him by snail mail in those days. We started writing to each other. I told him about some stuff that I'd been thinking about. He wrote back with very helpful comments. We ended up writing a couple of papers together before ever having met.
When you were in graduate school?
When I was in graduate school. I wanted to make those papers the basis of my thesis. I wasn't allowed to in the PhD program where I was. But when I got my PhD, Aharonov offered me a postdoc in Tel Aviv, which I was very happy to take. And I really had a sort of apprenticeship with him. Also, while I was in Israel, I met a lot of philosophers. And I began to get more of a sense that a philosophy department, as well as a physics department, might be a place I would think about trying to work. At the end of this postdoc, Aharonov also had a position at the University of South Carolina in the United States, which was at that time, because of Aharonov's presence there, basically the only physics department in the United States that was ready to support and encourage this kind of work. Aharonov was very generous to me and sort of got me a tenure track position in the physics department there. That was in all sorts of ways intellectually very nice, but South Carolina just wasn't the right place for me to live. I was very much of a New Yorker. I was very attached to New York, blah, blah, blah. South Carolina was a big, big culture shock, much bigger than, say, Tel Aviv was, or something like that. So I was, on all sorts of personal levels, eager to get out of South Carolina. At the same time, like I say, by this time, I had gotten to know a lot of philosophers. I had gotten to know a little bit about the professional structure of philosophy. And there were lots of people who were urging me to think about, whether a philosophy department might be a good place for me to work. It just so happened that people heard that Columbia was looking for a philosopher of science. Also, at the same time, they were looking for a philosopher of science at Berkeley. People pushed me to apply. I got both of them because of New York. I was more eager to come to Columbia. That's how I ended up in a philosophy department. It wasn't really at all that the focus of my interests had changed. These had always been my interests, and not only, and also I knew them to be interests that are properly identified as philosophical sorts of interest. I mean, I had a sort of high school kid's acquaintance with, say, the critique of pure reason, or something. I knew that people were interested in the history of philosophy, in what time was and what space was, and how this hooked up with scientific theories available at the time, and so on and so forth. So it wasn't a surprise to me that my interests in physics had a philosophical flavor. What I didn't know until I was well out of my PhD was that, as I said, the contemporary professional structure of philosophy was such that it might not be crazy for me to apply for a job in a philosophy department. So the actual transition to philosophy, if there was one, wasn't an intellectual event. It had mostly to do with wanting to be in New York. So no, there wasn't a story of an intellectual transition there. It goes without saying, once I did take a job in a philosophy department, there was a lot of philosophy of science and so on, which I was expected to teach and which I had to master and which I hadn't done before. So my acquaintance with philosophy had to quickly become much more systematic than it had previously been, and much more thorough than it had previously been. And figures, especially like Barry Lower, were these sort of father figures. It was so great to have someone, Barry in particular, who you knew you could go to with the stupidest question in the world and the most naive question in the world, and the question that you would have been embarrassed to raise with anyone else. And Barry was just amazing to me for that, and very much engineered the logistics of my transition from physics departments to philosophy departments. It was very much Barry who had heard about these jobs and was coming to me and pressing me to apply for them, and so on. So people were really, really nice to me, and I had lots of help. But it didn't represent a shift in my interests. It represented a shift in my understanding of, of the modern structure of universities, and in my understanding of the, nature of disciplinary boundaries and the kind of department in which it might, in which people would be most encouraging of interests like that.
Mm-hmm. I associate you so strongly with Columbia that it is very funny to imagine another possible world or concrete branch of the multiverse, if you're Sean Carroll or somewhere else, where you're at Berkeley.
It is bizarre. I mean, how, I grew up in New York, and when I was in high school, there was a program on Saturdays called the Science Honors Program for nerdy kids who were interested in science in the New York area. I was in that, so I started coming to Columbia, taking those classes on Saturdays when I was in high school. I was at Columbia as an undergraduate. Yeah, I've been at Columbia for an enormous number of years. Yeah.
Well, the last time we talked, it was with Tim Maudlin. I'm sure that viewers of this program know Tim Maudlin. But we had discussed doing an episode on the measurement problem, but we ended up talking a lot about Bohr and some other episodes in the development of quantum mechanics. But I think I began that episode or that conversation by asking whether you thought it would be a good idea to begin by situating the problem historically at all. Do you think that that might be worthwhile?
Let me see. Maybe I could start out by saying succinctly what I think the problem is and how it arises, and then maybe situate it historically.
Yeah, that sounds good.
If you think
that sounds good.
So look, here's the basic problem. If I ask how I know there's a chair or how I know there's a table in the room in front of me, we think we have a sketch of an answer to a question like that. There's light in the room, some of the light bounces off the table, some of that reflected light, enters my eye, produces certain electrical excitations in my retina. Those excitations in turn produce certain sorts of expectations in my optic nerve, and those produce further such excitations in my visual cortex, and yada, yada, yada. And there's a whole chain of physical causes and effects which eventually get my brain into that physical state or one of that set of physical states associated with seeing a table in the room. And similarly, if I ask, say, how I know that a certain subatomic particle just whizzed by along this trajectory, well, I have some bubble chamber or some spark chamber which reacts in a certain macroscopic way. If such a particle passes through it, there's a trail of bubbles or something like that. Then some of the light in the room bounces off the bubbles, or the sparks emit light, or so on and so forth. And the rest of the story is the same as with the table. And it goes without saying that our conviction is that all of the steps in these chains that I just described occur in strict accordance with whatever the fundamental laws of physics may happen to be.
I grant this so far.
And the thought is that it's a very firm expectation we have of our scientific investigation of the world that it's going to show us that it's going to be able to tell us a story that has the general form that I just described, of how I know there's a table in the room, or how I know a certain subatomic particle just arced by in this way. That's going to be, that can be told in principle in as much detail as we like, in as much detail as is requested, thoroughly in accord with those fundamental laws. And the short way to describe what the problem about measurement is in quantum mechanics is that the story, or the story format that I just described, radically breaks down in the case of quantum mechanics. And that's very surprising, that's very unsettling, and it amounts to a problem that you have to figure out what to do with, okay? Let me say a little more about the way in which it breaks down.
Yeah.
One of the very striking distinctions between classical physics, the physical picture of the world that comes out of Newton and goes, it's the physical picture of the world that people were slowly building up from Galileo and Newton through the end of the 19th century with figures like Maxwell and so on. It has several, I don't know how to characterize the classical view of the world succinctly, but, um, but, well, maybe this is helpful, okay? Newton had the following thought, or the following thought is implicit in what's now called the Newtonian picture of the world. All the material objects in the world consist ultimately of point particles, okay? And these particles move around in space according to the Newtonian equations of motion, F equals ma, okay? And if you want to know about the behaviors of tables or chairs or desks or cars or people, all you have to do in principle is analyze those objects into their constituent Newtonian particles, see how those particles are moving around. The laws of the motions of these particles, according to Newton, are fully deterministic, okay? If you know the positions and velocities of all the particles at some initial moment, and you know what kinds of particles they are, that is, what their electric charges are, what their masses are, so on, so that you can calculate the kinds of forces that they're exerting on one another. Everything is determined by those initial conditions. Good. As you go through the 18th and 19th century, you need some tweaks on that that have to do with phenomena of electricity and magnetism. It turns out that in addition to these particles, there's pressure on you to countenance the existence of other kinds of fundamental physical things called fields. These get affected in various ways by charges and motions and so on and so forth. And by the end of the 19th century, you have this physics of this soup of fields and particles, okay, moving around according to Newton's laws for the particles and Maxwell's equations for the electric and magnetic fields. And they constitute together a deterministic account of how everything evolves. So basically, forget about the electromagnetic stuff. If you're on the Newtonian picture of the world, what it is to have a complete history of the world is to have a list of the positions of all the particles in the world at all times, okay? That's the complete history of the world. Given that information, where every particle in the world was at every particular temporal instant, you can read off where the tables and chairs were, where the universities were, who got married to who sued who said what. These can all eventually be reduced to claims about how these point particles are moving, okay? In philosophical terms, we say all the other language we want to use about the history of the world supervenes on the language of the motions of these particles, can be read off in principle from the information about the motions of these particles. That's what the world consists in. You want to know the possible situations that the world could be in? It's all the possible positions in space that the particles could occupy at any particular moment. You want to know the possible histories of the world? It's all the possible motions that those particles could execute from t equals minus infinity to t equals plus infinity. That's the fundamental metaphysical structure of the world. Good. What's often considered striking and unsettling about quantum mechanics is that at the beginning of the 20th century, people start doing all kinds of experiments where, unlike in the Newtonian case, where we're just taking it for granted that, yeah, you look at these little dust motes or something like that, how they're moving around. They themselves presumably consist of billions upon billions of these elementary point particles, which we can't actually see. We're sort of taking it for granted that things are going to work out. In the beginning of the 20th century, people fooling around with cathode ray tubes and stuff like that begin to be able to keep track of the motions of individual elementary particles. And these particles are behaving in ways that are almost inconceivably bizarre, okay? In particular, people manage to convince themselves by doing lots of experiments with these elementary particles that things like electrons, for example, could be in, it's possible for an electron to be located at this point in space, and possible for an electron to be located at that point in space. Those are the familiar Newtonian possibilities, here or here or here or here or here. What these experiments at the beginning of the 20th century suggested to people, and I'm condensing here 30 years or so of wrestling with the results of these experiments in the beginning of the 20th century. There are certain sets of experiments, so-called interference experiments, double slit experiments, if you can read about this, want to read about this in the literature, neutron interferometry experiments, stuff like that. There's a whole family of experiments which slowly persuades people that that apparently there are certain states that electrons can be in, electrons and neutrons and all elementary particles can be in. Once again, there's a possible state where the electron is at point A. There's a possible state where the electron is at point B. What people became convinced of is that in addition, there are possible states of electrons such that the very question, is it located at point A or is it located at point B or is it located at neither of them, fails to make sense, okay? That the question, that there are certain situations in which the question, is the electron in box A or in box B or in neither of the boxes, is like is like a question of the form, is the number 5 married? Okay, or what is the weight in grams of Catholicism? Okay, or something like that. Questions that philosophers often refer to as category mistakes. Okay, that there can be situations of a material particle, an electron, okay, where asking whether or not it's in box A is somehow like asking what the marital status of the number 5 is, or what the weight in grams of Catholicism is, okay? This strikes people as absolutely bizarre. People felt forced to conclusions like this because if you tried to tell the story of these experiments in a way that used locutions like, well, at this point in the story, the electron, I suppose, must have been here. Or at this point in the story, the electron must have been there. Or even if you just insist that at this point in the story, there must be some place where the electron was, because after all, it got from here in the beginning of the experiment to there at the end of the experiment, it must have gone by some particular route, either through this route or through that route. You try to insist on that. You try to tell yourself a story about how these experiments went, okay, that's consistent with the results you got. You find that every particular claim about which route the electron might have taken somehow collapses into nonsense, becomes inconsistent with certain of the results of these experiments that you actually did, okay? So an idea grows up. That it appears to be a feature of the way these fundamental particles behave, that for every pair of states that such a particle could be in, that is the state of being located at A and the state of being located at B, there's also another radically unfamiliar but physically possible state, which is referred to as the superposition, of being located at A and being located at B, or the quantum mechanical superposition of being located at A or being located at B, which we can argue from our experiments is not a case of being located at A, and not a case of being located at B, and not a case of being located at both A and B, as you often find in the popular literature when they try to talk about superposition. And that's very bad too, and that would reduce the mysteriousness of this way below what it actually is. What these experiments suggest is that it is wrong to say under those circumstances that the electron is located at A, and that it's wrong to say that it's located at B, and that it's wrong to say that it's both at A and B, and that it's also wrong to say that it is neither at A nor is it at B, okay? If you think there must always be a fact of the matter about where the electron is, that exhausts the logical possibilities, okay? And so people felt forced to acknowledge that what these experiments seem to be screaming at us, okay, is that for any two states that an electron could be in, A and B, there are other physically possible states which can't be rightly characterized by saying that they're at A, can't be rightly characterized by saying it's at B, can't be rightly characterized by saying it's at both, and can't be rightly characterized by saying it's at neither, okay? And rather, you seem to be confronted with a situation in which asking whether the electron is at A or B is like asking about the marital status of the number 5. Okay, it's just a nonsensical question. Good. Good. Now, suppose we've absorbed that. Okay.
By hypothesis.
By hypothesis, by stipulation. Suppose we've absorbed that. Suppose we've begun to get used to that. Suppose we say to ourselves, well, okay, I guess at the subatomic level, things are very strange, okay? And questions about material bodies that has always seemed obvious to us must be sensible questions, can under certain circumstances fail to be sensible questions. Good. Anyway, this is this phenomenon of superposition, which is often cited as the most striking departure quantum mechanics makes from the classical picture of the world, from the picture of the physical world that we had before these experiments in the beginning of the 20th century. Good. Suppose we had learned from our laboratory experience how to produce such superposed states, okay? We had learned from ample experience that if you hook this cathode ray tube up to this magnet, yada, 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 you're going to end up with an electron that's in a quantum mechanical superposition of being located here and being located there. Okay, good. Moreover, a whole mathematical formalism was developed, quantum mechanics, which proved itself enormously successful at predicting when these superposed states would arise, under exactly what physical circumstances they would arise. An apparatus that is a mathematical apparatus for predicting, given some initial setup, how a certain later set of measurements would come out, so on, including the sorts of sets of measurements that had forced us to take this notion of superposition on board in the first place. So people developed, again, over the first 30 years of the 20th century, this very, very powerful algorithm, you might say, for predicting the outcomes of experiments. That is, this is an algorithm into which you input the physical details of how an experimental arrangement is initiated, okay, and gives you as output predictions about what later measurements on that, how later measurements on that physical system would come out. The predictions it gave you turned out to be probabilistic, turned out to be chancy, differently from the predictions of classical mechanics, which are always in principle deterministic, okay? But given this phenomenon of superposition, this chanciness is the least of our problems, okay? Maybe there's some chanciness there. That's not nearly as conceptually unsettling as this phenomenon of superposition. Good. But anyway, we got this algorithm. We also were able to show that as the material objects involved get larger and larger, the predictions of this algorithm approach more and more closely to the predictions of classical mechanics, Newtonian mechanics, okay? So there was reason to begin to think of this algorithm as the fundamental physical theory of the world, okay, that applied to everything, okay? It also applied to things like baseballs and planets. We had been using Newtonian mechanics very successfully before that to talk about the motions of baseballs and planets. And among the things that the quantum mechanical algorithm did for us is explain why Newtonian mechanics was as successful as it was, even though in principle it was incorrect. Okay, one could show how the predictions of quantum mechanics, as people say, reduce more and more precisely to the predictions of classical mechanics when you get into the regime of macroscopic objects like tables and chairs and baseballs and planets and so on and so forth, reduce more and more precisely to the predictions of Newtonian mechanics about those things. Good. So we're very puzzled metaphysically about what this talk about superposition means, okay? But at the same time, we have our hands on an algorithm which is predicting when these superpositions are going to arise and when they're not going to arise, okay? Which is getting which, for whatever input we put in, is giving us what appear to be correct probabilistic predictions about how the experiment is going to come out, whether the experiment involves subatomic particles or baseballs or spacecraft or whatever you like, okay? So there's this funny situation, okay? There's some obvious sense in which we don't understand the claims that this theory is making at all. Okay, but there's some other sense in which we've got a really powerful theory here, okay, that is giving us really good predictions about how appropriately specified experiments are going to come out, okay? Good. And the thought was, quantum mechanics is our new candidate, a candidate that supplants Newtonian mechanics or supplants the combination that we had at the end of the 19th century of Newtonian mechanics and Maxwellian electrodynamics and so on and so forth. This is our new candidate for the fundamental universal theory of the world. Okay, we knew of no experiment, okay, neither the ones that confirm classical mechanics nor the new ones where the behaviors of subatomic particles are not behaving in classical ways at all. We knew of no experiment whose outcomes didn't appear to be correctly predicted, at least in a probabilistic sense, by this new quantum mechanical algorithm. Good. So, well, like I've said already a couple of times, this is a funny situation. There's some sense in which we don't understand what this theory is telling us. There's another sense in which Well, I'm not sure how to put in English what this theory is saying, but whatever it's saying, it's right. Okay, good. Here's a curious thing. The following is our experience in the laboratory. Take an electron which has been prepared to be in a superposition of being here and here, and measure its location. Okay? Go look in this box, see if it's there. Go look in that box, see if it's there. It turns out that when you do that, sometimes you find it here and not there. Sometimes you find it here and not there. Okay? So the act of looking, okay, seems to change the state of this electron from a superposition of being here and here, in which there is simply no fact of the matter about where it is, okay? Just as there's no fact of the matter about the marital status of the number 5, okay? When we actually go and do a measurement, we do find it either here and not there, or there and not here. So we say, I see. So this act of performing a measurement is not just a passive process of taking in information. It seems to be producing a distinct and radical change in the state of the system that we're measuring itself, okay? That before we did this measurement, before we sort of asked by looking, is the particle here or is the particle there, we're convinced that we have good reasons for denying that there was any fact of the matter about where it was, okay? But it's also part of our laboratory experience that when we go and look, sometimes we find it here and not there. Sometimes we find it there and not here. We never find a situation when we look for it that suggests that there isn't a fact of the matter about where it is. Even though various other experiments we could do on it at that point do suggest that there's no fact of the matter about where it is. Good. And one says, I wonder how that works. I wonder how it is that this act of looking at it manages to do what people in the field started calling collapsing its state, okay, into either out of being in a superposition and to either the state of being here or being there. How does that work? How does the looking at it do that? Let's analyze that in detail. Let's say carefully what we mean by looking. What do we shine a light at it, or we put some kind of detector there, so on and so forth. Okay. So it turns out that you can ask this question of the algorithm, okay? Suppose we design a certain kind of instrument, okay? Who's going to swing its pointer in this direction if the electron turns out to be here, and is going to swing its pointer in that direction if the electron turns out to be there. We input the detailed physical design of this mechanism into our algorithm. We say we start with a superposition of the electron being here and here. We turn on the device, okay? The pointer is initially pointing straight up, neither this way nor that way. And we ask, how is this system going to physically evolve? We ask this algorithm, which we now trust, how is this system going to physically evolve? Our experience in the laboratory is that when we turn this on, sometimes the pointer swings this way and the particle is found to be there. Sometimes the pointer swings this way and the particle is found to be there. Good. Let's analyze this from the point of view of the algorithm. Lo and behold, you do this analysis and the algorithm says, you know what? My prediction, the algorithm's prediction, is that in circumstances like this, the pointer is going to enter into a superposition of pointing this way and pointing that way, okay? And this seems to conflict with our laboratory experience, okay? It's not the case that the pointer is sometimes going to point this way and sometimes going to point that way. If the electron started out in a superposition, there's a simple mathematical argument, given the mathematical structure of this algorithm, that what the pointer ought to do for sure is go into a superposition of pointing in these two directions. And that's not what we appear to see. We say, let's press this a little further. Suppose we think of the scientist, the sentient observer, who's looking at the pointer. We consider her to be a part of the physical system as well, that's interacting with the pointer. Maybe that'll help clear this up. Let's throw the observer into the total physical system whose behavior we are using this algorithm to analyze. It turns out if you do that, okay, once again, the algorithm gives you an unambiguous prediction. Now, it would be a natural reaction to what I've said so far to say, I don't understand. How can they possibly apply this fundamental algorithm to a physical system like a sentient observer that consists of trillions upon trillions of it? What, you're actually doing those calculations? No, you're not. But you can give a very powerful argument from certain features of the deep mathematical structure of this algorithm, in particular from a mathematical feature of this algorithm called its linearity, okay, that is going to tell you things even about what the observer's brain will do under these circumstances. And it turns out that the unambiguous deliverance of this algorithm is that the observer who is looking at the pointer ought to end up in a superposition of taking herself to see the pointer pointing this way and taking herself to see the pointer pointing that way. And at this point, your intuition simply revolts, okay? Well, that's not what happens. Okay, and what would it even feel like if that did happen? Okay, what would I get nauseous? Would I mean, I don't even know what we're talking about here, but I do know that that's not what happens when I look at those pointers. I can tell you from my extensive laboratory experience that when I look at the pointer in a situation like that, I either see it pointing this way and indicating that the particle is here, or I see it pointing that way, indicating that the particle is there. And I don't know what it would feel like to be in one of these superpositions of brain states such that there's no fact of the matter about whether I see the pointer pointing this way or pointing that way. But whatever it would feel like, it's sure as hell not the state that I end up in when I actually go and do these experiments. Good. This is the sense in which the story we started out with about how we know there's a table in the room collapses in the case of quantum mechanics, okay? In the case of quantum mechanics, if you tell the story step by step, in accord with what we take the fundamental physical laws to be, okay, the place you end up with is not the place you want to be. The place you end up with is not the brain state in which either you see the pointer pointing this way or you see the pointer pointing that way. That's not what the algorithm gives you. What the algorithm gives you is something that you know by experience doesn't happen, okay? Now, it might be easy to say, okay, so much the worse for this algorithm. The algorithm is obviously wrong, okay? We should throw it out and start with a new one. Well, that's a natural reaction. And in a certain way, I think that's going to be the correct reaction. But it's not a trivial one, because the extent to which this algorithm had been borne out, the accuracy of this algorithm had been borne out by all sorts of experiments, was tremendously impressive to people, okay? This algorithm was clearly the most precise, the most accurate physical theory that had ever made its appearance on the world stage in the history of human investigation. Okay, so so there's a real puzzle here. What are we supposed to do with the fact, okay, that that in circumstances like this, when the algorithm predicts that something is in a superposition and we look at it, we find it in one place or the other, okay? Good. And as I said a minute ago, it should be clear now what I meant in the beginning before we started talking about quantum mechanics at all. This aspiration to tell a story that starts with the table and the light in the room and ends up with my being in the mental state that I find myself in when I look in the direction of the table, this story is not going through in the quantum mechanical case. Good. Like I said, and now I'm going to talk a little about historical context.
Yeah. I'm glad, by the way, that we started the way that you
good,
preferred to.
Good,
absolutely.
Good. So you're confronted with this. This algorithm, which you think you have very strong reasons to believe, is the universally true fundamental physical account of the evolution of the world, is giving you wildly wrong predictions about what happens in this simple case, where you go and look at the electron that starts out in a superposition of being here and here. Once again, the natural reaction, the reasonable reaction, is, well, okay, it was a nice algorithm while it lasted, but something is obviously wrong, okay? And we're going to have to change it, okay? We should probably try to figure out a way to change it that doesn't mess up any of the predictions it makes that we know to be good, okay? But change it in such a way that it doesn't make this crazy prediction about what kind of mental state I'm going to be in when I look at this object. That's what I would characterize as the natural, reasonable, scientific reaction to this. This was not the reaction of the founders of quantum mechanics, okay? And it was particularly not the reaction of Bohr, okay?
Yes.
Bohr thought...
The Church of Satan, as you famously referred to him last time.
I mean, I don't... as soon as I say the words Bohr thought, I have to pause because it's very hard. He is very, very far from expressing himself in a uniform and internally consistent way. But let me do the best I can. Bohr thought that this was not a scientific problem, okay? That you should not be fiddling around like a nerd, changing this part of the algorithm or that part of the algorithm to get everything worked out, okay? No, this is the childish reaction. This is the stupid reaction. This is the shallow reaction to what's going on here. Bohr thought that it was a deep mistake and that one of the great lessons of quantum mechanics is precisely that it was a deep mistake. To have this even to entertain this aspiration of throwing everything into the physical system that we treat with this algorithm. You remember that we said, okay, we have this electron that's in a superposition. Well, what happens if we hook it up to one of these detection devices with a pointer? And now we're going to play the game of assuming that the detection device is another ordinary physical system. That is, all we're doing here is really calculating the results of some kind of interaction between two physical systems, some kind of a collision between two physical systems. If we want to figure out what's going to happen to the needle, you just treat the needle as another physical system whose behavior in interaction with this electron is something covered by this universal algorithm that we have. You plug it in, you grind it out, you see what happens, but you get an answer you don't like, that the needle is going to be in a superposition of pointing this way and that way. Then you say, okay, you know what? Let's throw the observer into this physical system too. Let's treat the observer as yet another physical system that's interacting with the pointer, which is in turn interacting with the electron. Put all three of them together, treat the collection of the three of them as just another, albeit very, very complicated physical system to which this algorithm should apply. And unfortunately, when you do that, you get an even worse answer, okay? That I'm going to end up in this brain state which doesn't correspond to either seeing the needle point this way or seeing the needle point that way. Good. Bohr thinks, like I said, what I would call a reasonable scientific reaction to this. Okay, something's wrong with the algorithm. Let's do some tinkering and see if we can fix it up. This was not Bohr's reaction, okay? Bohr's reaction was this thought that you can just take everything and throw it into the physical system whose behavior you're going to analyze, okay, by means of this algorithm, this is a mistake, okay? The idea that you think that physics, that any physical theory is going to give you a picture of what's going on that's complete in that radical way, okay, and that it even includes you doing the experiment and so on and so forth, this is a deep mistake. It wasn't obvious in classical mechanics that it was a deep mistake. In classical mechanics, we saw no obstacle to telling this story. The passing elementary particle causes a spark in the spark chamber. The spark emits light. The light enters my eye. Causes excitations in my retina, causes excitations in my optic nerve, yada, yada, yada. You can tell the story right to the end, okay? Or at least there was no obvious obstacle to telling the story right to the end. Telling the story right to the end would be a mathematically very complicated job because your eye and your brain and so on are very complicated physical objects when you analyze them in terms of their elementary Newtonian particles. But in principle, it didn't seem like there was any reason why you can't tell a story all the way from the beginning to the end, okay? Bohr thinks that the lesson of quantum mechanics was that the very aspiration of physics to be able to tell a story like this from beginning to end was exposed by the development of quantum mechanics as naive, okay? As more than could reasonably be asked of a physical theory, okay? And he thought this amounted to the discovery of something very, very deep, okay? The way he put it was that before physics even gets started, before you're coming to apply your physical theory to a certain phenomenon or a certain object or so on and so forth, before that process even gets started, in order to get it off the ground, you need to divide the world, as it were, into subject and object, okay? You need to make a division of the world into the stuff that, as it were, is standing in front of your measuring apparatus and the stuff that's standing behind your measuring apparatus. And what you aspire to apply your algorithm to is only the stuff that's standing in front of the measuring apparatus, okay? And when the measurement takes place, that's when the application of the physics ends. The physics gives you probabilities for how this experiment is going to come out, but the idea that the fact of its coming out is also something that the physics can describe should be given up, okay? This is something that certainly, prior to quantum mechanics, physics was much more ambitious than that, okay? The thought was, there's nothing special about calling something a measuring instrument. That just characterizes it as a physical system with a particular structure, which you can analyze using the fundamental physical laws, just like you could analyze any other system. Bohr thought that the lesson to learn from quantum mechanics is that that's not right. There can't be a sort of theoretical physical description of the entirety of the universe, including whatever it is that you use to measure that universe, including your brain, so on and so forth. If you don't first put a cut, okay, and agree to some convention about what the algorithm is going to be applied to, what stands on this side of the measuring apparatus and what stands on this side of the measuring apparatus, you can't even get started. I mean, here's a, whoops, I'm sorry. Let me just, is it okay if I read something?
Oh, please.
I think this is a passage that I also read in our last conversation with Tim, but I think it captures, you know, like I say, who the hell really knows what Bohr had in mind? But here's the penultimate paragraph, or excuse me, the next to last paragraph of Bohr's famous response to the EPR, the Einstein-Podolsky-Rosen paper, which is one of the few places where he's thought to have tried to take some care to spell himself out explicitly. Bohr says, this necessity, the one I was just referring to, this necessity in each experimental, this necessity of discriminating in each experimental arrangement between those parts of the physical system which are considered which are to be treated as measuring instruments, and those which constitute the objects under investigation, may indeed be said to form a principal distinction between classical and quantum mechanical descriptions of physical phenomena. It's true that the place within each measuring procedure where this discrimination is made is in both cases largely a matter of convenience, while, however, in classical physics, the distinction between object and measuring agencies does not entail any difference in the character of the description of the phenomena concerned. This is what I was saying a minute ago. Its fundamental importance in quantum theory, as we have seen, has its root in the indispensable use of classical concepts. I'll say something about this in a minute, in the interpretation of all proper measurements, even though the classical theories do not suffice in accounting for the new types of regularities with which we are concerned in atomic physics. In accordance with this situation, there can be no question of any unambiguous interpretation of the symbols of quantum mechanics other than that embodied in the well-known rules which allow to predict the results to be obtained by a given experimental arrangement described in a totally classical way, and which have found their general expression. That part is not important. By securing its proper correspondence with the okay, actually, that's as much as is going to be relevant to our conversation here. Bohr thinks, whereas in classical mechanics, there's no need to make such a discrimination. In quantum mechanics, there absolutely is. And so the very idea of a total description of the world in terms of our fundamental physical theory makes no sense, okay? Simply makes no sense. Let me say a little bit about this classical language. Here's what Bohr, I think, thought was going on. Bohr had some idea, and this kind of has an almost tragic structure to it, okay? Bohr thought that the following two things were true. One, the use of the language of classical physics for describing things like pointer positions or outcomes of experiments was ineluctable, was unavoidable, okay? Was inescapable, okay? That's the language we use, and that's the language we must use, okay? In order to record the outcomes of experiments, in order to communicate the outcomes of experiments, in order to reason about the outcomes of experiments. Why he thought this was unavoidable, why he thought it wasn't possible to learn the quantum mechanical language and start using that, I have to say I just don't have a clue, okay? But he was very sure of this, and this was very important to him. And this gives rise, like I said, to a kind of deep philosophical, tragic tension, okay? Which is the following. These classical concepts are utterly indispensable for the purpose of recording and reasoning about and communicating about the outcomes of these experiments. And on the other hand, they are absolutely inapplicable as you know, they are incapable of being put to work in order to describe the behaviors of these subatomic particles that we're doing measurements on, okay? So the thought was, in order to reason about, record, communicate about the results of these experiments, we must speak as if the material body must always be here or here, okay, and not in any superposition of the two. But insisting on that will make it impossible for that language to describe the behaviors of these systems that we're doing experiments on, okay? So there is this tension buried in the very concept of the scientific project itself, which is for the first time showing its face with the advent of quantum mechanics. And this is not something to be gotten over or to, you know, this is, you know, in Heideggerian language, not to be bypassed, okay?
It makes sense why this is called the foundations of physics.
Right. You can't get past this. And this has the consequence that in order to do science at all, there must be a part of the world, our measuring instruments, ourselves, that we're talking about in non-quantum mechanical language, okay? So you have this tragic, necessary incompleteness of the fundamental language of physics, okay? This is very obscure. This is, just as a historical matter, Bohr's, through his education, was very much influenced by Hegelian language, was very much influenced by Kierkegaardian kinds of language, and so on. And I think, now I'm just purely speculating, but I think historians ought to look into this. The first astonishing thing to say is, okay, Bohr is talking this gibberish, okay? I just read you a passage. It's sort of like listening to the ravings of the oracle at Delphi, or, it's very hard to understand exactly what's going on here, exactly why it's inevitable that the language in which we describe experiments has to be a classical language. Why can't we learn why can't we go native and learn the quantum mechanical language? So there are all these obscurities. Surprisingly, the reaction of the entire community of theoretical physics was, yes, absolutely. Bohr is the deepest thinker we have, and this is exactly the right way to think about quantum mechanics, okay? And I mean the level to which Bohr was revered by the whole community of theoretical physics is mind-boggling, okay? The guy was clearly, people often play a parlor game. Who would you most like to have over? Which historical figure would you most like to have over for dinner, okay? I'd like to have Bohr over for dinner because I don't know how he did this. The guy was clearly, a person with a kind of charismatic power that's difficult even to imagine. Because you read the writing, there's just nothing there to go along with. There's no boat there to jump on. I mean, you don't know what you're doing. His personal presence seems to have had an enormous effect on people. It happens again and again and again in the first half of the 20th century that this or that figure, a leading intellectual figure of the 20th century, a leading theoretical physicist of the 20th century, goes for a walk in the woods with Bohr for half an hour, and their life is changed. Really? Okay, and yeah, so I would have loved to have met him because I don't understand how he did this. Because if you look at what the content of what he actually says, there's nothing appealing there. There's nothing there's nothing. You don't. There's nothing seductive there. Okay, I don't feel it. Okay. Good. And what I was going to say was, and like I say, this is pure speculation. This was all taking place in the intellectual atmosphere, in the cultural atmosphere of the rise of modernism, especially high literary modernism. Okay? Which all these people were very aware of. And you can't help but think, that these quantum mechanics guys said to themselves, you think you have a crisis of representation? Like to people like Joyce or Kafka, or you think you have a crisis of you don't know anything, okay? We got a crisis of representation. It's not about human motivations, it's about rocks, okay? You try to represent rocks, you fall into hopeless paradox, and so on and so forth. So I think there must have been something of this. There was some idea that this is how you can be cool in the early part of the 20th century in Western Europe. Who knows what the motivations were? I would bet that there's something like this going on. But anyway, for whatever reasons, Bohr propounds this, okay? People who wanted more understandable accounts of what was going on were rather brutally suppressed, okay? Bohr had all these dictums, a profound truth, a trivial truth is a truth whose negation is false. A profound truth is a truth whose negation is also true, okay? Or clarity tends to crowd out depth, okay? I don't know what to do with this, okay? I guess I'm in the wrong university building. I wanted clarity about what's going on in the world. Clarity crowds out depth. Okay, I'm sorry. I guess I ought to go to some other building. I thought the physics building was where I was going to find clarity. Okay. There are a few people, very few, and very persecuted, that is, they can't get jobs and so on and so forth, who say, gee, I don't know, it seems to me that the right response to this measurement problem is to say there's something wrong with this algorithm. And that one of our demands ought to be, yeah, if this is really the fundamental physics of the world, we ought to be able to treat the universe as a whole, including ourselves and our measuring instruments and so on, as a physical system whose behaviors can be accounted for by this theory. That's what we want from a physical theory. You're telling us we're stupid or naive or not sufficiently modern to want this from a physical theory? Well, sorry. That's what I want. Okay? And there were people, especially early on, like David Bohm, okay, who were trying to figure out what kinds of modifications of this algorithm could turn it into a theory, at least for which there was no principled reason, like in the classical case, to think that anything stood in the way of applying it to the universe as a whole, as a physical system. Okay? That is, the search was underway for what came to be referred to as quantum mechanics as a universal theory, okay? Or a way of understanding quantum mechanics, or something like quantum mechanics as a universal theory, okay? An enormous amount of time went by before there was any consensus in any identifiable corner of the physics or philosophy community. Like I say, there were these individuals in the wilderness, okay? But before there was any consensus, I mean, it was really the 1980s or something like that, before there was an identifiable group of people who said, I'm sorry, I guess what I really wanted from physics was a universal theory. And if this can't be a universal theory, then it is defective in some way. And the thing to do is to get a better theory. Good. And people discovered that there were actually people like Bohm who had proposed such theories, and then other people started proposing other such theories from the 1980s onward. And there is now, I think it's fair to say, among people who study this seriously, a consensus. So the idea was, Bohr had declared this measurement problem, this is not a scientific problem. What this is, rather, is an encounter with the limits of the scientific project.
Right.
Okay? This is an encounter for the first time in physics of the point beyond which the scientific imagination is incapable of penetrating into the world. Okay? So there was in the period, I would say, from the 80s through the end of the 20th century, there was a big fight being waged by people like Tim, by people like me, like Barry, like other people, urging people to think of this as indeed a scientific problem. Okay? It's not an encounter with the limits of the scientific imagination. It's just a case of a defective scientific theory. Okay? And what we need to do with such a situation is figure out how to fix the theory. Okay? Not declare that this is our encounter with the ineffable, that that scientific realism had itself discovered that realism was impossible, or something like that. And it was the idea, I think I was saying this in our last conversation with Tim, it was the idea that a question like that was at stake that that made me think, that's what interested me about the foundations of quantum mechanics. Okay?
You've come full circle.
Yes, right. So, I think it's fair to say that among people who study these questions seriously, there's been a dramatic sea change over the past 30 years or so, okay? That it is a scientific problem. And like I think I was also saying last time, one of the funny things about the role of philosophers in this is that you had Bohr announcing this is not a scientific problem, this is a deep philosophical discovery, okay? And you had philosophers like Tim and me and Barry saying, no, this is not a philosophical issue, this is a scientific problem, okay? And the appropriate reaction to this problem is to figure out how to fix the theory we have, okay? Because there's something defective about it. There isn't a defect here, as Bohr was arguing, in the conception of the scientific project itself, okay? That's what Bohr was arguing had been discovered here. A defect in the very conception of the scientific project itself. Okay? Whereas people like us were arguing, no, where are you getting this from? It's a defect in this particular theory. Let's approach this situation the way we approach all such situations in science. Our theory is making wrong predictions. Throw it out and replace it with a new one. Okay? Fix it. Okay? It's a scientific problem. Good.
Something, I'll jump in here. Something that I just find very interesting about this, given the conversation I was just having in this room before we started with Peter Boyd about string theory, is you qualify this as a scientific problem because it emerged out of experiment, and we need to come up with a better theory to account for that.
Right.
But in the case of string theory, granted, I'm not an expert and this is just one interpretation of the issue, all the developments of string theory came very removed from experiment because the standard model can account for all of the observations.
Right.
So this, lends credence to some of these arguments that string theory is not science. And
I mean, maybe. I think those are... that's a slightly different topic.
Yeah.
But I can. I mean.
I don't want to take you too far away from quantum mechanics.
But just a quick comment on that, and I don't want to set myself up as an expert on string theory here, also, which I'm not. But string theory is, for example, among what's supposed to be the triumphs of string theory, okay, is that there should be a particle like a graviton, okay? That is, that there should be gravity, okay? That seems to me a striking explanation of our experimental experience. If people want to whine, that doesn't count because we knew there was gravity already, I don't understand why they're getting so excited about that. The idea that there could be indirect ways of empirically confirming even a theory like string theory, it certainly hasn't been made obvious to me that that's not possible. Maybe the experiments are very challenging now. Maybe they won't be on the scene for years or generations. This is also true, and this gets us back to our topic. There have been several proposals about how to fix quantum mechanics so as to solve the measurement problem, to solve it in the sense of solving a scientific problem. So there have been several proposals about how to solve the measurement problem. We can discuss them in some detail if you'd like. But there have also been these different proposals make different empirical predictions. They're genuinely different scientific theories. On the other hand, it happens that it happens to be a feature of the proposals that we have so far, that the experimental predictions where they differ, okay, are experiments that we're not even remotely in a position to do right now because of technological limitations, okay? And that we may not be in a position to do for generations, okay? I don't, if somebody says that makes it unscientific, I don't really see why. Life can be tough, okay?
Yeah.
And it's not, and it may turn out that some of the experiments that you really need to do in order to answer questions that you're really interested in are really, really hard, okay? Even with string theory, I mean, once string theory gets to a point of development where it's making explicit predictions, these predictions may not be, it may not be possible to make them manifest in experiments that we're capable of doing right now. I don't understand why that shows that string theory is unscientific. Life is tough, okay? Science is hard, okay? Sometimes, it looks like you just can't do this experiment right now, or other times, and everybody certainly hopes this is going to happen in quantum mechanics, it looks like you can't do the experiment, but somebody gets a clever idea, somebody gets a way to trick these theories into exposing their differences in a way that's more straightforward technologically than people had assumed was possible. Everybody hopes this is going to happen, okay? Yeah, it may be that science gets to a point where you say, in order to be able to answer this question, we'd have to be able to do this experiment. And doing this experiment just appears to be centuries beyond our present technological capacities. I don't know what. Does that mean? I don't see why anybody would think that means it's not a scientific question. It does mean we're not going to be able to answer this question. And in this respect, the course of the scientific project has been, at least in this respect, disappointing, or ended up in a disappointment. But it doesn't seem to me to in any way impugn the status of these questions as perfectly scientific questions.
But some of the unintuitive features of string theory, such as the existence of these six-dimensional compact spaces, I mean, they're not pressed upon us by experiment the way that superposition was pressed upon us by experiment.
First of all, the question is how hard they're pressed, okay? These higher dimensions in string theory, nobody doubts, unless, we don't even have at the moment proofs that the string theories we write down are internally mathematically consistent, so on and so forth. So there's a lot of work to do there. But assuming they pass those tests, yes, in principle, these higher dimensions ought to impress themselves on us, in principle, by experimental means. But the experiments may turn out to be much, much more difficult than the experiments by means of which superpositions were impressed on us at the beginning of the 20th century. Like I say, I don't know what to say to that, except who told you this was going to be easy, okay? Sometimes, like in the case of superposition, things get pressed upon us in a way that's now very straightforward. We can repeat these experiments in laboratories very, very easily. But before the 20th century, we couldn't have done them, okay? We needed these cathode ray tubes. We needed this kind of level of control over electric currents and so on and so forth, which we simply didn't have before the 20th century. I don't, if somebody wants to say these kinds of situations in string theory raise the threat that that the scientific project as conducted by human beings is going to end up in a certain sort of disappointment, okay? In that we're going to realize we're going to be able to explain to ourselves why the answers to certain questions which are really basic and really important are going to have to await technological advances which may not come for centuries and centuries. That may very well happen. Who promised you it was going to be otherwise? So, yeah, hurling sort of insulting names like unscientific, that may be the way the world is. What are we supposed to do about that? Okay, it may be that there are very interesting and deep questions which we're going to need to wait for centuries and centuries of technological advancement to answer. Is that frustrating? Sure. Okay. Does that mean these kinds of theories are inappropriate objects of scientific speculation? I really don't see why. We're not hurting anybody, okay? Just trying to figure out what's going on in the world, and we got ourselves into this corner, and we can explain how we got ourselves into this corner, and we can say, look, from where we're standing now, it looks like we're going to need fantastically more sensitive measuring devices than we can even envision at the moment in order to answer these questions. Okay, okay.
As an outsider, I'm very interested in string theory.
Right.
But I'm very surprised to hear that you are as well, just because, I mean, I think within philosophy of physics or foundations of physics, the minority of work is being done on string theory and quantum gravity.
But that's just because the theory is not, I mean, this is something that I've often heard, say, Brian Greene say, who's certainly an enthusiast for string theory. He said, look, and I think he's sort of right, although there are some people who are doing it and who are saying some interesting things, but Brian tends to say, you know, I don't feel like we're ready for philosophy of string theory yet, or foundations of string theory. The theory is not remotely in the form that, say, the quantum mechanical algorithm was when we began to speculate about its logical foundations. The theory has to achieve a certain level of internal logical coherence, of conceptual maturity before it even makes sense to start asking foundational questions like, what is this really saying about the structure of the world? What is it saying, you know, the kinds of questions that arose in quantum mechanics about our relation to the structure of the world, our place in the structure of the world, so on and so forth. Often you just need to wait for the theories to develop some, especially in the case of theories that are not just experimentally challenging, but very, very, very mathematically challenging in the way that string theory is. There's just, I mean, this is a matter of taste, a matter of judgment, but yeah, there is a feeling with certain theories, it's too early. Let's let these guys go on for a while, see what they come up with, and a moment will come when it's going to be more ripe to ask foundational or philosophical questions about it.
Well, I very much appreciate your humoring this digression on string theory, but given that there are time constraints, and I want to make sure that we run more of the gamut on the measurement problem, I think now might be a good time, since we've covered the basics, we've covered some of the history with Bohr, to get into what's been happening, I mean, since the time period you mentioned, the 80s or so.
Yeah, so the idea was, you know, people like Tim and me and Barry and lots of other people spent years arguing that it was a scientific problem, okay? And I think that battle has been largely won by people who seriously think about this stuff. And you find very few people anymore who say they agree with Bohr or who even know what it is that one would agree with or disagree with if one agreed with Bohr. And then there have been various proposals about how to fix it. And there are three great traditions. So let me say a little more about the algorithm. The algorithm represents physical situations of the physical system it treats with a certain mathematical object called a wave function, okay? And it's an important principle of this algorithm that giving a wave function gives a complete description of the state of a physical system at any one moment. And the other thing that the algorithm provides is a set of laws about how these wave functions change with time under certain physical circumstances. Good. And like I said, the algorithm suggests that, for example, the wave function corresponding to a particle that's located at point A will have a bump near point A and be zero everywhere else. The wave function that represents a particle that's located at point B will have a bump near point B and it will be zero everywhere else. The wave function that represents a particle which is in a superposition of being located at point A and located at point B will have a bump at point A and another bump at point B and be zero everywhere else. So about this particle, we say it's not at A, it's not at B, it's not at both, but it's also not at neither, okay? Good. So you have these wave functional descriptions of physical systems. You have these dynamical laws which tell you how these wave functions evolve with time under certain physical situations. And this is the very, very bare bones of the logical structure of this quantum mechanical algorithm. Good. There are two obvious approaches to fiddling with this. So the trouble is, you know, when you hook up this pointer to the particle, when you hook up a sentient observer to the particle, the wave function of that whole system develops multiple bumps, you know, both corresponding to the pointer pointing here and the pointer pointing there, or both corresponding to the observer's brain seeing the pointer pointing here and the observer's brain seeing the pointer pointing there, and so on. Good. There's a famous, I guess, aphorism of John Bell's, where he says, look, what the wave function shows you must be one of two things. Either this description of the world by means of wave functions is incomplete, it leaves something out, or our claims about how the wave functions evolve in time are wrong, okay? And each of those locutions suggests a strategy for trying to solve this problem. So one way of trying to solve this problem, solving it by means of a so-called collapse of the wave function, is to say, look, what we have to explain in the case of a particle that's initially in a superposition of being here and here, and then you hook it up to a measuring device, and then you hook the measuring device up to a sentient observer, what we've got to explain is that something makes one of those bumps go away somewhere in that process, okay? We know that the algorithm won't give us that. The question is, can we fiddle with the algorithm a little bit? Can we add some small terms to the equations of motion, which won't make much of a difference in ordinary laboratory cases, but will suddenly start to make a big difference when you hook the thing up to a pointer or when you hook the pointer up to a sentient observer? Are there ways of fiddling with the equations of motion, okay, that are going to, in the appropriate circumstances and not in other circumstances, make one of these bumps go away, okay? Good. We now have, since the 80s or so, a really beautiful example of such a theory, okay? You might have thought such a theory was going to be really hard to cook up because you might have thought that the business of specifying exactly the circumstances in which you want one of these bumps to go away and the circumstances in which you don't want one of these bumps to go away might be hopelessly complicated. There are three Italian physicists, Gherardi, Ramini, and Weber, who had a really clever idea about how to tweak this differential equation that in the algorithm is supposed to govern how these wave functions evolve. It's a beautifully simple idea. I mean, people had been thinking about how to tweak it in this way for decades. And all of a sudden, they just suggested a really simple idea, and it was amazing. And you feel like the scales fall from your eyes. So we have a nice theory of collapses of wave functions along those lines. There are various now other versions of this theory, which maybe you can argue are better in some respects, blah, blah, blah. There are issues about how to make this theory compatible with the theory of relativity. It was originally formulated for a very simple non-relativistic version of the quantum mechanical algorithm. But anyway, there is a whole class of theories like that. There's another class of theories which says, no, 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 we're not going to tweak the equations of motion. The Schrodinger equation, which is the equation you find in the standard algorithm, is always going to give an exact description of the evolution of the wave function. What we're going to do is deny this other quantum mechanical principle that the wave function itself is always a complete description of the physical system, okay? We're going to say that, for example, in the case where you have a particle wave function which has a bump at A and also has a bump at B, there may nevertheless be a fact of the matter about where the particle is, okay? Because the wave function by itself is not a complete description of the physical situation. There may be some other variable, call it x, okay? Where, you know, the x is over the left bump but not over the right bump, and that means that the particle really is at position A, okay? Now, we'd have to know how these x's work, how they evolve in time, what their dynamical equations of motion are, so on and so forth. But anyway, this general strategy for solving the measurement problem is referred to usually as a hidden variable strategy, although hidden is a very bad word. I would call it an additional variable strategy.
Why do you not like hidden?
Because in fact, the claim of these kinds of theories is when you go and look for this particle, okay, it's this x that you see, okay? It's the opposite of hidden, okay? It's this x that you see, not the wave function itself, okay? Good. So a good description of them would be extra variable theories or additional variable theories. Theories that deny that the wave function is the complete description of the world. So like I say, in accord with this aphorism of Bell's, one obvious way to try to fix the algorithm is to deny that the dynamical laws that you find in the algorithm are correct, okay? And try to tweak those dynamical laws so that in cases of measurement, you do suddenly get rid of one of the bumps and hang on to only one. The other obvious way to try to solve it is not to fiddle with the dynamical laws, but to fiddle with the way the world is described at any given instant, to deny that the wave function is a complete description of the physical situation of the world at any given instant. We now have beautiful, although preliminary, non-relativistic, so on and so forth, but beautifully worked out versions of each of this kind of theory. Okay? What's widely regarded as the most successful theory in the collapse tradition is this GRW theory, various of its close relatives. And what's widely regarded as the most successful theory in this extra variable tradition is Bohm's so-called hidden variable theory. Good. There's also a third tradition, where a tradition that traces back to Everett, where you try to avoid both horns of this dilemma. You try to insist that the wave function is a complete description of the world at a time, and also to insist that the dynamical laws that you find in the original quantum mechanical algorithm are exactly correct. So then you say, okay, but then how does this work? What explains the fact that when I go measure the position of an electron, which is initially in a superposition of being here and here, I find it either here or there? Proposed answer, something very weird happens when you do this measurement. Nothing happens to the electron you measured. Something weird happens to you. You split into two selves, one of whom sees the electron here and the other of whom sees the electron there. Okay? And that's how to understand what the traditional algorithm is telling us. These are called Everettian, or more colorfully, many worlds attempts to solve the measurement problem. This comprises the third major tradition of attempts to solve the measurement problem. This would be done without actually tweaking the mathematics of the theory in any way. It would be done by re-understanding in a realistic way, okay? In a way, so the idea here is, no, we're not going to be like Bohr. Quantum mechanics tells us a complete theory of the world, okay? Gives us a complete description of the world, including measuring instruments, including observers, so on and so forth. The way you're going to solve the problem is by granting that the story that it does tell us about the world, which is a universal, complete, traditionally, philosophically realistic picture of the world, is that the realistic picture it's describing is incredibly wacky. Okay, we're splitting. Okay,
yeah.
There really are two. It really was the case that before we looked, there wasn't a fact of the matter about where the particle is, and as soon as we do look, there are two particles and two of us. One of which saw it here, the other of which saw it there. Blah blah blah. Good. Aside from being wacky, which is not a good reason to reject a theory, especially in the weird dark waters that we're facing, that we're navigating in quantum mechanics. But there are concerns, and I would say I have concerns, about whether this third tradition even ends up being logically coherent. Okay? That's a long story. There's a lot to say about it, but
I think our listeners might turn to our episode with Sean Carroll, where we talked a bit about these things.
Good. So there is, right. So you will have gotten into that with Sean. Sean is somebody...
We got into that, the three of us.
Right, that's right. Sean is somebody who very much hopes that this can be made coherent. I would say I'm skeptical that it can. So I think the right thing to say is that there is something like 2.5 great traditions of thought now about how to solve the measurement problem as a scientific problem. Okay, there is this collapse tradition. There is this extra variable tradition or hidden variable tradition, and there is this many worlds tradition. And we're now in the happy circumstance where really smart people all over the world are working hard at elaborating and precisifying and clarifying these proposals. And of course, everyone hopes that tomorrow somebody's going to come up with another tradition, okay? Specifically about the true traditions that I know make sense, the extra variable tradition and the collapse tradition, they make different experimental predictions. And we know exactly which experiments they make different predictions about, but we also know why those experiments are going to be very hard to do with currently available technology. Let me add to that in the last 30 years or so, experimentalists have been more clever than anybody expected or hoped that they were going to be. And the possibility of us actually doing some experiments which really will begin to discriminate between these two traditions, I think is something that people are more hopeful about than they were over the last 30 years. It still looks very daunting in all kinds of ways. We'll see, okay? I mean, what's true is that certain early versions of the collapse theories have already been ruled out by experiments that we've done, which is a very encouraging development. Still, we don't have experiments yet that can distinguish decisively between the extra variable theories and the collapse theories. But like I say, we know exactly what experiments we would need to do in order to make that distinction. We know exactly what the nature of the differences between the empirical predictions that these two sorts of theories make is. And it's just a matter of the fact that these experiments are for the moment beyond what we're technologically in a position to do. The case of the many worlds theories is a little more amorphous. I mean, if those theories are coherent, then as far as we can tell, their predictions will agree with the extra variable theories and will disagree with the collapse theories. But as I say, there's a question, at least in my mind, of whether they're actually coherent at all.
Is it the case then that there's underdetermination between the Bohmian theory and the many worlds theory?
And the many worlds theory? As far as we can tell at the moment, well, like I say, there's not underdetermination if the many worlds theory isn't coherent.
Right.
Okay. If I imagine a world in which the many worlds theories are coherent, okay, then insofar as we can see at the moment, and this is not a technological problem, this is a theoretical problem. Insofar as we can see at the moment, there is no even in principle possible experiment that could distinguish between them. So if the many worlds theories really are incoherent, then we're facing a real principled underdetermination.
And am I right that you're leaning more toward the GRW spontaneous?
No, I wouldn't say that.
Okay.
No, I would say that I'm pretty agnostic between collapse theories and extra variables theories. It's true that there are all kinds of ways in which, if collapse theories were true, they would be very nice. That would be a very nice thing vis-a-vis certain other areas of the foundations of physics, like the foundations of statistical mechanics and so on. That is, if the GRW theory were true, it would sort of revolutionize the way we think about the foundations of statistical mechanics in a very nice way. The way we think about it now, there are two completely separate places where chances fundamentally enter into the evolution of the world. If the GRW theory were true, it would collapse those two into one. So that would be very nice. But I don't, this comes in under the category of advice to God about how the world should have been constructed. I don't know if it's true or not, okay? If it turns out to be true, which is an experimental question, then it's going to have these nice consequences. I've worked on thinking through those consequences a lot, so it might look to people as if I prefer the GRW theory, but no, I mean, it seems to me the only honest answer is, how the hell should I know? This is an experimental question. Okay?
Yeah, I've speculated that based on what I'd heard that you were a fan of the GRW theory, so it's good to have this clarification.
Right.
But, I think it's worth bringing up, just since we were already talking about string theory. My guess is that string theory has to be agnostic on spontaneous collapse or hidden variable theories, just because if it weren't, a lot of money and thought would be going into carrying out these experiments, just because string theory has gotten so much flack for not making predictions.
No, that's a good, yes. I can't see why it wouldn't be the case that string theory is agnostic on those questions. Yeah.
One thing that Sean said the last time we spoke is that one of the reasons that he's returned to these foundational questions is because he thinks that they may prove the key to moving forward with these other questions like quantum gravity. I'm wondering if you feel similarly?
That would be great. I don't feel the kind of pressure that you feel more in a physics community, that you need some other excuse to be interested in these questions than that they are in and of themselves fantastically interesting questions, okay? Like I said, what interested me about foundations of quantum mechanics was that what seemed to be at stake there is the very viability of the scientific project itself, okay? I mean, let me put this maybe slightly more dramatically. And this is a way of saying, what does it mean to be interested in the foundations of physics? At least this is what it means for me. There are all kinds of scientific questions. How do rainbows work? How do galaxies work? How does cosmology work? Blah, blah, blah. Here's another scientific question, which I take it is the scientific question, and which is the one that was at stake in the foundations of quantum mechanics. Is the scientific project going to work out at all? Okay. The amazing thing about quantum mechanics, needless to say, there's a long history of philosophical critiques of something like naive metaphysical realism. Okay, there is, there's transcendental idealism, and there's everything under the, everything. There's a long history of philosophical critiques of the kind of naive metaphysical realism that you're usually taking for granted when you do science, okay, when you do physics. The interesting thing about quantum mechanics was that the critique was for the first time supposed to be coming out of the scientific project itself, rather than out of external reflection, philosophical reflection on the scientific project. The exciting thing about quantum mechanics in the lingo of horror movies was that the call was coming from inside the house.
Yeah,
okay.
Right.
And it was sort of the ultimate case of the call coming from inside the house. And This is what I take to be the scientific question, which at the end of the day is the really interesting one. Not what's going to be the correct scientific description of rainbows, or even what's going to be the correct scientific description of gravity, which is a much more profound question. But is the whole scientific project going to work out at all? Okay? Is it somehow going to run into a wall? Okay? Is it going to hit on something that it can't get past? Okay? This is exactly what Bohr thought had happened in the case of the measurement problem. And it's what people that I work with and admire over the course of my career have spent much of the career arguing did not happen. Okay? The scientific project as originally envisioned, according to these people, is alive and well. Okay? We got plenty of unsolved problems, but we do not have what Bohr thought we had, which is that the scientific project in some decisive way ran into a wall, okay, which it's not going to be able to get past. Okay? So for me, the great scientific question is the question of whether this project is going to work out at all. Okay? That's what I take to have been at stake in the measurement problem. You want to know why I was interested in the measurement problem? Because I saw that as being at stake. Because Bohr said that's what was at stake. If this helps solve the problem of quantum gravity, and it's not unlikely that it will help with that, because people are more and more convinced after having spent so many years unable to get to the bottom of quantum gravity that the only way to get through this is going to be to take very carefully apart what we mean by quantum mechanics in the first place, and so on. So it may be very important to solving that problem, but my interest in it has to do with its having an impact on an even bigger problem, and what I would think of as the scientific problem. Science, as I understand it, is the investigation of the question of whether the scientific project is going to pan out, okay, or whether it's going to get stopped someplace. Okay, we were told in the beginning of the 20th century that it had been stopped. Okay, and you know, like Mark Twain said, it turns out that the reports of its death had been greatly exaggerated. So if it helps out with quantum gravity, that's great. And I don't think it's implausible that it's going to help out with quantum gravity. It's certainly fooling around with very fundamental stuff in the immediate neighborhood of what we think we need to understand in order to solve quantum gravity. But I don't feel the need to justify my interest in it because of possibilities like that. It's coming to you right in the face. It's the question of, can the thing succeed at all? Okay? Are we ever going to be able to think of everything, tables and chairs and measuring instruments and ourselves, as encompassed within some fundamental unified scientific picture of the world? That's what interests me about all this.
Great note on which to end. I mean, like I said at the beginning, I don't know how many times you've been on the show, 5 or 6, but it has been so fun to finally do this in person.
Great,
and
for me too.
It's a
great.
Thank you so much, David.
Nice.